class, we'll look at state estimation. State estimation. So almost everything in the class so far has been about controls, but estimation is very important, especially when you have noisy sensors or you don't have certain measurements, as we'll see later. So we'll look at the spring mass system we've looked in the past. Okay, this is 2 degree of freedom system. Let's say Q1 and Q2 are the 2 degrees of freedom. And there is a force on mass 2, and then there is a shared force on mass 1 and M2, such that it pushes M1 to the left and M2 to the right. Okay, now we had written down the state space equations for the system. They are AX plus BU equals X dot, where X was X1 dot, X2 dot, X3 dot, X4 dot equals 0, 0, K1 divided by M1 plus K2 divided by M1, K2 divided by M2, 0, 0, K2 divided by M1, and minus K2 divided by M2, then 1, 0, 0, 0, 0, 1, 0, 0. X1, X2, X3, X4 plus BU, and B is this 0, 0, minus 1 divided by M1, 1 divided by M2, 0, 0, 0, 1 divided by M2. And then the 2 controls were U1, U2. Okay, here X1 was Q1, X2 was Q2, X3 was the rate of change of Q1, and X4 was rate of change of Q2. Okay, for such a system like this, we had figured out that we could use either pole placement or LQR to compute gain K, right? This K, once we have the gain K, we can then control the system in the way we want. So what's X? It's minus K, X1, X2, X3, X4. So this will be U1, U2. And K will obviously be 2 cross 4. So when you multiply it by 4 cross 1, you get 2 cross 2 times 2 cross 1, and that would be the 2 controls. So one thing we note here is that in order to do feedback control, you need to have estimates of X1, X2, X3, and X4, where X1, X2, X3, X4 are the positions, Qs, and Q1 and Q2, and the velocities, Q1 dot and Q2 dot. If you want to physically build a system like this and control it, what you would have to do is measure these 4 things, which means that you'll have to have 2 sensors to measure the positions and 2 sensors to measure the velocities. So you need 4 sensors to, in order to estimate the position of and velocity and then do control. But then you can see that you really don't need velocity as well as the position. The velocity is the derivative of position. So if you have a position sensor, you can estimate the velocity. Or if you have a velocity sensor, then you can estimate the position by integrating. So really, you don't need 4 sensors. You only need 2 sensors, and you can estimate the remaining 2 using something you know about the system. So let me put that down here. We need all 4 states for control. Okay, this means that we need 4 sensors so 2 for position and 2 for velocity. Okay, but clearly this will make it expensive. So what we do is, since we know position is related to velocity, we can get away with only 2 sensors and estimate the remaining 2. Okay, this obviously will make the design cheaper, and being cheap is very important, especially if you want to do a mass production, right? You want to keep the design as cheap as possible. Also, if you want to put more sensors, it means there's more tooling needed in order to figure out the sensor location. So we can estimate position from velocity and vice versa. So what we'll do is we'll use this variable y as sensor measurements. Okay, and for this example, we will assume we have velocity sensors installed. Okay, so the same arguments will go with the position sensors. So I'm doing this for velocity, but you can use the same arguments and use the same design techniques as I show for velocities. So the measurements are a function of the state x. In this case, we are looking at linear estimates, but it need not be linear. We'll not worry about linearity for now, non-linearity for now. So we need to figure out what C is such that we can get the 2 position measurements. So we know that x is x1, x2, x3, and x4. And then remember that there are 2 sensors for the 2 positions. This is fixed as 4 cross 1. So we need to put a matrix which is 2 cross 4, right? 2 cross 4, so that when we multiply it with 4 cross 1, we have 2 cross 1. And those 2 rows corresponds to the 2 sensors. So we have velocity measurements. So x3 is the velocity, x4 is the velocity. And so what we'll do is we'll put 0, 0, 1, 0. So it gives me x3 and then 0, 0, 0, 1. So if you do the math, you'll see that it comes out to be x3, x4. So y equals x3, x4. And people would write that in a more general way as c times x. Okay, so that's the standard way to write it. Okay, now, as I said, our goal is given x3, x4, we want to estimate x1, x2. So, okay, we want to estimate x1, x2 from measurements of x3, x4. And let's do one thing. Let's just make our notation for estimate to be the state variable with a hat. So estimates are x1 hat, x2 hat, given x3 hat and x4 hat, which are measured. Yeah. I stated that in order to differentiate between the actual state and the estimated states, we will put a hat on the estimates. Yeah, those are measurements, but the measurements may not be the actual state because the measurements would have some noise. So we'll just make it x3 and x4 hat. So our estimated state is x hat, which is x1 hat, x2 hat, x3 hat, x4 hat. Okay, so now one way of doing the estimates is that we have a model of the system. So x dot equals ax plus bu is the true system. And then let's say that we have perfect estimates of the dynamics. So we know A and B perfectly. And so we can say x dot equals ax hat plus bu estimate. So why don't we just use this equation, which is we know something about the initial state, x hat, x0 say, and then we can just integrate the equations to compute x hat as a function of time. The problem with that is that this is going to give you a big error in some cases. So let's compute the error between the actual system. Here in this case, we know the actual system. And we also know the estimate, but we're just trying to see what will go wrong. So if you take the difference and then you take the derivative of the difference, you can write that substituting from that equation, we have ax plus bu plus ax hat plus bu, and then the bu cancels. And so we're left with should be minus a times x minus x hat, which is a times e. So we see that E dot equals A times E. So the error basically grows or shrinks depending on A. Now we know something about system stability when we have a system like E dot equals AE or X dot equals AX. If the system is stable, then all the eigenvalues of A should be less than 0, right? Should be negative half plane. If that's not true, then the system is unstable. So what will happen here is that as long as the eigenvalues of A are negative, you're good. Your estimates will probably work. But if the eigenvalues of A are positive, then you see that your estimates will grow exponentially fast, which means that if there are small errors, let's say your initial estimate of E was off by delta of 0.1, it'll actually grow exponentially with time. So it's a good technique, but doesn't work when the system is unstable. So for a stable system, it will work. So this error depends on A, which is the system dynamics. If A is unstable, E will also be unstable. Okay, so it's not a good thing to use this method of estimating the state. Okay, so what people do is there's something called an observer, which will fix this problem. So next we'll look at what is known as a Luenberger observer. Now this is for a deterministic system. What I mean by deterministic system is that every time you give an input to a system, you'll get the same output no matter what. In contrast to this is a stochastic system where if you give an input, you may get either the same or a different output. Okay, most things in the world are stochastic, not deterministic. But let's do the deterministic. You can assume system to be deterministic if you see that the variability is substantially low, right? So what you normally want to do is, if you're given a problem, you first hit it with this technique of a deterministic observer state estimator. If that doesn't work, then you want to go to more complicated things. And we'll be talking about a more sophisticated method for stochastic system a little bit later. Okay, now here is what is the Luenberger observer. So we consider the following estimator. Okay, x dot equals AX plus BU plus L times Y minus Y hat. Okay, it seems very random. So we took the system dynamics and added to it L, which is gain, user defined gain, and we talk about how to compute that. And this is going to be error in measured state and estimated state. Okay, so why this choice? Let's see what is the consequence of using this choice. So let's first simplify this. X dot equals AX hat plus PU plus L. We know that Y equals C times X. Y hat equals C times X, but since it's an estimate, it's going to be C times X hat. Okay, let's move things around. So we have LCX. Then let's club all the terms involving hats plus A minus LC times X hat. And then finally, we left with B times C. Okay, so this is the dynamics of our estimator or the state estimator. Now, when you see it, it does not look any way like our original system, which was X dot equals AX plus B. Let's see what happens by looking at the error. So error is X minus X hat like before. Error dot is X dot minus X hat dot equals. So I just need to plug in these values. X dot is AX plus BU. That's a true system behavior. And then subtract from that this term, LCX minus A minus LC. LCX plus A minus LCX plus PU. Okay. Okay, now what we can do is this BU will cancel with this PU because of the negative sign. And then we can club this AX with this LCX. And so we'll have A minus LCX. And then we have minus A minus LC. This should be hat from this hat. Okay, so the error dot equals A minus LC X minus X hat, which is E dot equals A minus LC. Okay, now we have, remember we earlier had E dot equals A times E, but now we have E dot equals A minus LC times C, which means that now the stability of the system will depend on the eigenvalues of A minus LC. But to our fortune, L is a user-chosen gain, which you can choose. So you can tune whatever you want to make that system be stable. So we will choose choose L. L to place the eigenvalues of A minus LC far away on the negative half plane or negative plane, which means that I'm going to make the system stable by choosing L. Okay, now, just like we talked about something similar for system gain k. Remember, we had an equation which was x dot equals a minus bkx, and we talked about that system is by nature a may not be stable, but a minus bk can be made stable because you can choose the gain k. We talked also about controllability, that is what is the condition on a and b such that you can find a gain k. Turns out, just like that, there is a term called observability, which tells you if you can actually observe all the states. So you're given measurements of some states. Can you estimate other states? You can, only if the system is observable. So let's define observability, because that's something which you want to first check before you do any design. So observability. Okay, the definition is a linear system is observable if and only if any initial state x of 0 can be reconstructed from the output at some time t. So phi of t within a finite time t. So it's like it's saying basically that if you're given the state or the observation y at some time t, you should be able to go back and say what was the state at some time t equals 0 or t equals 1. Okay, if you can do it for t equals 0, you can also do it for t equals 1. Okay, and then I gave an example of, if you do not have for the controllability, I gave an example that if you have a steering and if you have on a, I think it was a tricycle or a Dubin's car where you can steer and also change the speed of the wheels, then you can basically go anywhere x, y, and state space, right? And if you don't have one of them, you cannot do that. So there's a similar analogous thing here. That is, if you don't have those types of measurements, then you are not able to measure those. So for example, in this case, if you only have measurements for the positions and velocities of one mass, then you probably cannot estimate the position velocity of the other mass. Now that's probably not true here because the system is coupled, so if moving one moves other. But in extreme position situation where the spring constant becomes less and less stiff, you can imagine that the motion of, so let's say that you know Q2 and you know Q2 dot, and the only way of estimating Q1 is through K2, but if K2 becomes less and less stiff, then you will see that M1 will stop moving, right? Because there's no interaction. And so you will not be able to measure or estimate Q1 and Q1 dot based on Q2. That's because what happens in principle is that this coupling term goes to 0. So X3, the systems are not coupled and you cannot observe it. So how do you check observability? Well, there is a similar test. It's called test of observability. You compute the observability matrix. It's given by this expression. So you keep multiplying A with C. So that's the observability matrix. Then you compute the rank of the observability matrix. If the rank is n is the system state. So in this case, the system state is 4. Then the system is observable. If it is less than n, then the system is not observable. Okay, and I just would say that this OB is also known as observability matrix. Okay, so what you'll do is, just like controllability, you will compute, well, you first import the control library, you'll compute or set up A and C, so just define them using NumPy array. Compute the observability. It is available in control library by saying control.obsv, and then you provide it with A and C. And then to check the rank, you go to NumPy and then use dinalg matrix rank. Okay, and then that will give you the observability. Okay, so you want to do this test before you do any sensor or state estimation, because if it's not observable, then you'll just be wasting your time trying to observe the system. Now, if you noticed, there seems to be some similarity between controllability and observability. Okay, let's look at the controllability expression. It's A, B, so on till A, B, n minus 1. And observability was defined as C, CA, CA squared, so on till CA, n minus 1. Okay, they look very different, but what if I take the transpose of OB? I get C transpose, CA transpose, CA square transpose, so on to CA n minus 1 transpose. Now, this is something which you proved, I think, in the first homework to numerical examples, that the AB transpose is same as B transpose, A transpose, and so we can use that here. This is same as C transpose, A transpose, C transpose. You need to do this multiple times for A square, so you write it at C times A, then take them two at a time, reverse them, but you can show that it comes out to be A square transpose, C transpose, so on, A n minus 1 transpose, C transpose. Okay, now if you look closely, this expression and this one, you can make a correspondence, right? You can see that controllability is similar as observability transpose, provided, a mistake here, this should be, yeah, this is my bad, this should be B. This is not A, it should be B. Okay, now if you compare them, you see that compare 2 with 1, you see that that's true, provided B equals C transpose and the A equals A transpose. So this, all this here comes from controllability, everything here comes from observability. So don't get confused with A equals A transpose. A is not A transpose, but the way you can make a correspondence is you take the A from observability and take the transpose and match it with the A from the controllability. That's what I mean by this. So that's not true that A is same as A transpose. Okay, which means that if you want to actually check for observability, you don't need to use OBS. You can actually use CTRB, which was used for controllability. All you do is you compute OB transpose. It comes out to be control.CTRB, which is controllability. But now the A and B are replaced with A transpose and C transpose. Right? Normally we did this. dot CTRP A comma B. But since A is A transpose and B is C transpose, you can do that. So this will give you the first, these expressions are the same. And then you can check the rank of OB transpose and then you get the rank. Okay, so now that we have established that there's a dual between controllability and observability, now let's go back to where we had taken a diversion, which is we said that we can pretty much control this L and hence place the eigenvalues wherever we want. So let's take that idea by comparing these equations. X dot equals A minus BKX, and in order to place the eigenvalues on the left half plane, what we did was we used place with A and B, right? So we can do something similar here. We look at E dot equals A minus LCE, and then take the transpose of both sides. We have A, E dot transpose equals A minus LC transpose E transpose. This comes out to be A transpose minus C transpose L transpose. Again, I'm using the fact that LC transpose is C transpose L transpose. Okay, now we can again do the same thing, compare this with 4. Okay, so again, we have A equals A transpose, X, E. A from here is the same as A transpose for E. The B is the same as C transpose, and K is the same as L transpose. So in order to place in order to choose the eigenvalues of A minus LC, what we do is we use the same command place, but replace A with A transpose and B with C transpose. And this will give me L. That actually gives me K. So it'll give me L transpose actually. So once you get L transpose, you need to take the transpose again to compute L. So this is how you can place the poles of the observer, and then that will actually help you to estimate the states which are not estimated. And you can then, I'll show you an example where you can actually place the poles wherever you want, and it actually does a good job of estimating. I forgot one argument here. This is P, should be a P there, which puts the poles wherever you want them to be. These are user chosen locations. User chosen. So ideally you want to place the poles far away from the origin. Now, unlike gains, if you remember the discussion we had, if you make the gains too high, you'll see that the control becomes very aggressive. That is not true for observers. In fact, I would highly recommend putting the gains as far as possible because that really doesn't affect the control or the estimates. It actually makes the estimates go much, much faster. I think there is some limit to it eventually because of the bandwidth, but you normally want to try to have as big poles as possible for placement of the gain L. Okay, now let me show you an example how to do this in Python. Yeah. What's that? The last part is we are trying to design an observer gain L, and you would do it with place. So this is the equation. So this is the equation. We know what K does. It basically controls how fast you can stabilize the system. What this equation does is it tells you how fast you can estimate the unknown states. So in order to estimate the unknown states fast enough, you need to choose the gain L. And the way you can choose L is using place by noticing that this equation looks a lot like this equation, but if you take the transpose. Actually, it will become clear. Let me show you an example where it will become clear numerically. So this is a spring mass example. I just correlate the same A, C, the same things which I wrote down. What I do here is compute the eigenvalue of the uncontrolled system. Then I create the observer. I show you how to do the alternate version of the observer by using CTRV instead of OBSV. You can actually check if they give you the same answer. So I've done that here, but I've commented it out. You can place the poles. I place the poles at -5, -6, but you can place them wherever you want, and that gives you the gain. So Control-Shift-B. There's nothing kind of other than just numerics here. It's computing. Okay, so it just sort of confirms that you put the poles where you want. Now, the more interesting thing is I then use this code to test out the spring mass name, spring mass system. There's no damper. Okay, so what I do here is I have simulated the system over a time period. I only use estimates from the velocities. I have copy-paste the gain from the previous code. Yeah, and I just show you how to do that, all that. The first line is basically X, the actual system. The second line is X estimated. And then I need to integrate all the equations here. Now, if you have a true system, if the true system is not known to you, you wouldn't integrate that. You will integrate the estimated system. So what I have here is first, I think I do this without, okay, so comment this out. Okay, so what I do here is there's no observer. So you can see that's A and A. And then I can set, what I did was I set the initial condition to be 0.5. So I take one of the mass, move it by 0.5. But the other one, I have an estimated error. So it's not moved to 0.1, 0.5 or 0.2. That is, I think that it is 0.2, not 0.5. So now what will happen is it will try to estimate the state based on that information using no observers, just the integration example I talked about. And you can see it's way off. The red is true and the blue is the actual. So the estimates are way, way off, right? The red is not lining with the blue. Now what I can do is the same system, same initial condition, turn on the observer. This is on. And now you see that the red and blue are practically on top of it. In fact, starts here, and then in no time it's back. And remember, I just placed the poles at -5. I could have done even faster job of getting them back by putting it, say, -20, -30. So that just shows you how an observer works and how it's able to estimate the states, which you have not measured. Okay, now let's do stochastic system. This will be the last step. I'll stop, and next week we'll get to 3D. We'll get to 3D robotics, 3D dynamics, and also we'll start with the project. I'll tell you more details about the project next week.